see the presentation?
Yes.
All right. All right. Well, let me go back. Just so everyone knows, my name is Kobe Adams. I am the Director of Customer Support here at SambaNova Systems. And so I'm one of the ones that I engage with along with Jimmy when you have issues with things. So one of the common items, when people are dealing with developing their own models and running them on our platform is, maybe they have a little bit of performance issues. So we're going to go ahead and look at what you can go through and measure and get information on using our SambaTune profiling tool. So we're going to go over the goals, the performance profiling methodology, SambaTune usage, and a bit of a demo. All right. So the SambaTune system model performance profiling methodology is best described in the documentation. So I could have gone through and taken the documentation and just completely copied and pasted over to the deck, but instead I'm going to go ahead and walk you through the documentation as we go through that. So our documentation is located at docs.sambanova.ai. So if I go back to the root of the documentation, and then you can see the SambaTune documentation, and the latest release version is 1.18. Go ahead and make that a little bit bigger so it's not so much of an eye chart. But basically, one of the main things is when you're going through this is run with a sufficient number of iterations. By default, if you don't specify or anything like that, we do about 100 iterations. Now, if you have an extremely large model that each iteration, takes 3 or 4 days, then yeah, we understand. Don't run with 100 iterations. Use a little bit of, good practice and resource utilizations when going through and set this up. But by default, for smaller, quicker running models, then we do say, do 100 iterations to go through and gather sufficient data for the tool to do its job. Then the basic workflow is to look at, okay, are you host bound? Yes or no? All right, so we will have a host bound section, and then you go through and look and say, okay, we can look at the typical things like Pi instrument and other profiling uses to see, okay, where is that time being spent on the host, and how do I go through and tweak and modify my model, or modify my batch sizes, or modify, different model parameters in order to reduce the amount of time on the host. The ultimate goal with any of your models, if you're running them on a SambaNova platform, is have as much time on the RDU as humanly possible. Okay, time spent on the host is effectively wasted time. One of the main things that we see that is a main victim of that is if in your code, you are constantly transferring tensors back and forth between code that's executing on the RDU and code that's executing on the CPU. For example, if you have a custom loss calculation that you're running on CPU and you're constantly having to toss your tensors back to the host to run that custom loss calculation, you need to evaluate. It's like, is it really necessary for me to have that? Or is that something that maybe I can run at the end of an epic or whatever to get that information versus running it every, say, iteration? Okay. Now let's say that's not host bound, and you're mostly on the RDU like you want to be, and then you're like, it's still not fast enough, right? Okay, then what we do is when we go ahead and we compile your model, we break it apart into sections. For your smaller models, you're going to have 3 basic sections. You're going to have your forward, you're going to have your backward, you're going to have your optimizer. All right. And you'll see those effectively numbered, 0, 1, 2, inside the log files and also inside the different graph information. And then you go look and say, okay, where am I spending most of my time? In your larger models, there could be models, especially in some of your larger LLM models, that are broken up into 30-something sections, 100 sections. And then you can go through and look and drill down into that particular section. And then that will sort of map back to a particular function or operation inside your model code. All right. Are you consuming, a whole lot of time in a softmax? Are you consuming a lot of time in some sort of linear transition and stuff where it's having to copy, a lot of data through to memory or whatever? You can go through and identify, those sections. All right. Now then our sections are further broken down into stages. Okay, and so we can go through and drill down and look into the stages and just sort of get more and more granular as you go through the graph. The one thing that the tool does not do just yet is it does not give you a recommendation. So ultimately what you're going to do is if you profile and you find yourself this far down the rabbit hole into a particular section or a particular stage that's having an issue, is you're going to open up a support ticket to us, and we're going to assist you with analyzing the graph output and give you recommendations, on how to improve that. Now, another thing also with if you have stage latencies that you go through, you're going to check your section PCU usage. You want to try to see if your PCU utilization is greater than 90%. So what you're going to do then is look for compute bound sections. So let's say that the compiler went through and it didn't actually break the model apart into highly optimized sections for laying out on the graph. You could see where you have these individual PCU bottlenecks, and then you can work with us at SambaNova System to define human definition files in order for us to manually split those sections apart to limit those bottlenecks. Okay. All right. I'm going to go through here into the workflow overview and just sort of drill down a little bit. And once again, here's the top-down thing. So we're going to go through and we're going to look at the graph, but let's just go ahead and look at it as side by side and these explanations in the doc before we drill down into the demo. Again, start by iteration. So select the next tab and check the graph summary. So you can see here, let me expand this so it's a little bit bigger. You can see here that in this particular one, there's more time on the host than on the RDU. So we're going to do that. If the model is not host bound by RDU, then you're going to click on the RDU bar in the GUI and drill down into that. And then drill down into your latencies, into your stage reports, and then if the section of stages seem balancing, you can click your overview and then go through and drill down into particular latency stats. So you can see our latency, our PMU utilization, PC utilization, DDR utilization, etc. Here are some examples on optimizing host-bound models. All right. Do you have are you COM function bound? Are you spending most of your time in conversion functions? So this is where if you are doing a lot of FP, doing FP16, and instead of 32-point precision, and we're going ahead and we're converting if we're having to convert the precision of those buffers over as part of the model work, then that's going to show up in the COM function bound. Data transfer bound, that's the thing I was talking about shipping tensors back and forth to the host. So you're going to want to reduce the number of times you have output tensors going back to the host. You really just sort of want to do that at the end. You don't want to keep constantly doing that through your model unless you have some logic or code that necessitates that. All right. Then you have a section called SambaBound. So that's our code. So that's the conversion where we're taking your Python and going through and actually executing it. If you're bound in this section, we'll have a PyInstrument tab, which will go down and basically look like any other profile tool and show you the functions that are taking the most time. More often than not, if you're down in that area, you're going to be opening up a support case saying, hey, your sample function here is taking, way too long. Help me figure out why. Right. Okay. Setup bound, very rarely do you see this. Setup bound is so the initial time to actually load the model onto the processor. So taking our actual path, loading it onto the RDU and laying out the graph, right? That's the setup time. And then you have the Python to C bound. And so that is the actual time, sort of you see this mostly on the first iteration of the model. The amount of time from converting from Python code over to the C execution of the on the actual RDU. All right, so let's go ahead and take a look at some examples here. Let's go back into the deck for a second. All right. I'll go back. I'll go back for a second. So that was the documentation. So now we're going to go into the usage. All right. Let me get my my little Zoom thing out of the way there. All right. So this does not need to be run as root, but it was in this example because I'm a bad citizen. I was on a machine that was running as root when I should be running as an end user. SambaTune does not run via Slurm. Okay, so especially in the environment that you have at Argonne, you would have to go through and run an salec command and specify the node that you want to reserve, node or nodes that you want to reserve, and then you will log into that node and run the SambaTune scripts on that node that you specified in this salec. And then you can see here the salec is going to drop you into a bash shells on the particular node or nodes that are in the node list. And then when you're done running your SambaTune, you need to make sure you exit this bash script. Otherwise, it's never going to release the resources back to the environment. All right. Another thing that you need to set is a dump root and an artifact root environment variables. So in this case, I'm just setting dump root to PWD. If you want to do it via artifact root, you can pass artifact root on the command line. All right. So you'll see here that the command is as simple as running SambaTune, which is underneath the ops SambaFlow directory, and then passing it a config.yaml. And we'll go ahead and we'll look at some of those YAML files. So here I'm showing I'm doing an execution, but hey, I didn't throw it a YAML file, right? It's like error, the following arguments required. We need a config, it's got to have something to read to try and execute. So let's look at a sample config, right? So this is, for a very simple linear net micro model that's underneath our micros, okay? So this and as we're cutting the YAML, it's telling you that, hey, this requires a SambaFlow apps micros package to be installed. Obviously, you cannot use this YAML file unless this package is installed, right? And then the app paths to the default path for the apps install. Now, typically what we do, because we really don't want people modifying the source app packages that are under ops SambaFlow apps, etc. You can have micros, images, NLP, et cetera, all the various different applications that can be installed. We don't want people modify them there. So typically what they'll do is if there's a particular model they're working with, they will copy that model down to their local home directory, right? All right, so here you pass in your model args. So these, when you're looking at model args, these are the standard args, the minimum args that are required for either running or compiling a model. For the compile args, for compile specific args, we're passing in this case a -- plot, which will allow it to gather more additional information about plotting out how the graph is being laid out. Now you'll see here run args num iterations 100. Okay, you don't necessarily have to specify this, and in fact, if you do a run without this, it will default to the number of iterations to 100. But like I said, if you have a very large model where each iteration takes forever, you're going to want this number to be rather low. Okay. All right. So then the env arguments are exactly that. So if there are some standard environment variables that you pass for your model for optimization, like these are standard ones that we pass through just about every model that we run, then you're going to want to go ahead and set those environment variables there. Okay, here's a little bit more complex one. This one is actually doing a compare. All right, so this is effectively the same thing going against the linear net model, but it's going through and it's comparing different batch sizes, different mini batch sizes, different sizes for your input and output features, right? So we're basically effectively it's going to do 2 runs with these different options and give you outputs that you can go ahead and look at and compare and say, hey, which is sort of the best way for me to run this model? And this is one that's probably utilized the most, because they're like, especially if it's a new model that you're developing, it's the first time you ported it over, you're running it on RDU for the first time, and you want to see, okay, what is really the most optimal way to go ahead and run this thing? All right. Now, this one it's an abbreviated version, but I wanted to show you how complex these config files can get. All right. If you're on one of the Argonne systems, you can go to the ops SambaFlow SambaTune configs directory and see the whole thing yourself. But effectively, if I tried to put this on slides, it's about 3.5 to 4 slides long. So as you can see, if you were running a more complex model with HT files, with compiler config files, et cetera, you will specify all that information in here and then go ahead and execute the SambaTune. That will go ahead and bring all this information in. Right? And you see here, this one wants, a lot more. Whoops, sorry about that. This one wants a lot more environment variables, et cetera. All right. All right, now we're going to go through and we're looking at an example. We have different modes. So basically, run is a full training run. All right, exactly what it implies. Now, if you do a run, you're not going to get excessive instrument and benchmark data, but you are going to get real-time data on how it. You're going to get excuse me, sorry, you get real-time data on how it is utilizing the RDU and the PCUs and PMU sections, et cetera, and your true DDR bandwidth times back and forth and your PCI times back and forth. Benchmark is effectively running a measure performance. So if you put a benchmark in your model does not have a measure performance section, it's not going to work. Okay. The other item is instrument, which is that's a fine grained performance counters on the hardware per section and per stage. Okay. And then there is a parameter sweep option that you can specify. And that is where you can go through and tell it to, hey, sweep through different parameter combinations for this model. Now, when you go through and do when you go through and do any of these, the first step that it's going to do is it's going to compile a path on the fly. If you have a model where the path compilation time is excessive, is going to take a long time, you can actually pass a path that you already have compiled into the SambaTune process, and it will go ahead and use that, and it will save you a little bit of time on your SambaTune run. All right. Next, if you're doing parameter sweep, we'll obviously have to go through and compile a path for each combination of parameters that you have in your parameter sweep. All right. All right. Oops. I think that's it. Yeah, here's an example run where with instrumentation and all performance counters command. So here I'm telling this, I want it to go through and run this config. I want it to run in benchmark mode. I want it to run in instrument mode, and I want it to run in run mode. Okay. This will go through, and obviously it is going to be multiple runs, and it will also be multiple paths. So it'll be a path for sort of each stage of these. So again, if you have a model where it takes a long time to build the path, you're going to want to pass it in, the location of your paths that you've already done. All right, SambaTune report. So obviously, I'm getting ready to show you a UI that you can go through and take a look at things. But a lot of people are actually more interested in the raw data, the JSON files, the CSV files, all that different type of stuff. That is all there. So remember how we were talking about dump root / artifact root? Effectively the same thing. Underneath there, you will wind up with what is called a SambaTune gen directory. And then you will have a directory that is the month, day, hour, and second of, that should have been minute. Sorry about that. Of and the model name, and then the reports. And underneath there, you have the subdirectories, and you can go through and look at the various raw files. If you have your own analytics tools, or you like to go through and build your own graphs and charts, have at it. All the raw data is there for you to play with. All right. Now the SambaTune UI. Now it's available as a Flask HTTP server using Unicorn from the bare metal install, or as an installable wheel file for Linux and Mac. Okay. Windows port is on the roadmap, but it does not work yet because it uses Unicorn at this moment instead of Waitress. Unicorn is not supported on Windows. However, if you can run a Linux Docker on your Windows system, then you could do that there. Once the wheel file is installed, it's just effectively going ahead and running SambaTune UI, and then you're going to point it at that SambaTune gen directory that you just created. And by the way, if you have like a common NFS share that is between your servers and your client machines and everything like that, make that the location for your dump root in your SambaTune Gen. And you every run you do, you can dump under the same, dump root, and then you can go through and have look in the UI, and you'll see in a second where it'll list the ones that are under there, and just look at whichever ones you do have a historical representation, obviously with the caveat unless you run out of storage space on your NFS share or wherever you're storing it at. All right, now if you run and execute, you can, obviously this tool is installed on the data scale system itself. And what I'm getting ready to run and show you is launching it from there. If you choose to let your users go through and execute it from the data scale system, then you have to go through and assign a port number to each one of your users. Because if one user is up running on 8576, the default, another user cannot be up and running on that port. So if you're going to let them run it on the data scale systems, you're going to have some sort of system in place to assign each user their own SambaTune port number. Does that make sense? Look at the demo. All right. So here you see I am in my one of my SambaTune Gen subdirectories here, but I just went ahead and launched the UI and I pointed it at my SambaTune Gen directory, and you can see that it started up the Flash server. The username is always going to be admin. The password is a UUID that is generated every time you launch the thing. So if I kill the server and relaunch it, all right. Then you will see that it generated a new password, and it will do that every single time. And that is by design. Okay. So then we will go through and let's go back to here. And you see here, refresh. So we'll go to admin. Let's go ahead and pick up what that password was. All right. Did I pass it the right directory? Yeah. Live demo is fun, huh? What did I do? Hang on. Okay. Here's that.
It could be somewhat similar error to what Jamie ran, Kobe. So
It's there. I'll just do it again. That was weird. That was literally the first time I've ever hit that. That's what always happens with live demos, right? Hmm. At least you know that I'm not faking it. What is going on? It's only worked every single time that I ran it today.
Oh, wait, there's a message in the chat.
Hmm. What do you mean? What do you mean by that? Let me see this. Well, here we go. Live debug, right? Well, that all looks good. Okay. Time. Shouldn't have killed.
Toby,
Shouldn't have killed it.
it could be something wrong with the node. What I was wondering if we can say like
Yeah, let me cover this.
around the
I
base
can,
cases, maybe we could try it redo these demos again.
yeah. Let me go ahead and I'm going to try one more time.
Okay, sure.
And if not, then what I'll do is I'll copy it over to S1 and then try it from there. And okay, that's what I expect to see. All right, take 3 or 4, whatever we're at. I literally was just in here 10 minutes ago. Or maybe 20 minutes ago. Did I get the wrong one?
You have missed the 18th thing.
I missed the 8. Copy and paste fail. This does not make sense. Let me try some. Oh, you know. And if you do have, let's see if I can trick it. Okay, I will be troubleshooting that later. But so somehow it got confused, even though I passed it in the proper directory. And by going through and choosing update and then repointing it at the exact same path, I got it back. So good, I don't have to move systems, but I will be troubleshooting that and filing the necessary engineering investigations when complete. Let's go ahead and let's look at one of them first. All right, so we're gonna go one of them standalone. So this was run using a compare YAML file where it had 2 different sets of parameters. All right, so this went through and showing, so this is the one that was with batch size of 1024, MB of 128, 520 and 512. Let's go ahead and, by the way, you can look at these things. These are just the host information about the host that it executed on. The dynamic information is it's really just going to go through and show you, the number of RDUs available on this node and stuff and everything that was sort of real time while you're running. And this is sort of the same information in static, which should be there. Typically, these should not differ. If these differ, then you probably have a hardware problem somewhere, but they should not differ. And let's go back to the configuration. Let's go ahead and look at the analytics. So the first thing the analytics is going to do, it's going to go ahead and is going to drop you into the hardware latency window. Here you can see on this particular model, it's a small model, that most of the time is in host, and the RDU time is about 18%. Saying host could be a bottleneck. Let's go ahead and look at the host analysis below. If I go here and I look at my host model, you can see here that I have transfers taking like 48% of the 2. You might want to check the tensor tab, the tab above, and then I have 36% in comm functions. You know, this is effectively, this linear model is not written very well as far as keeping all the work on the RDU. It's sending a lot of information back and forth as the model is running back to the thing. All right. So here I can go here and I can look at you know, the number of bytes that are going through the different functions. And so here you can see it's the linear outputs 0 that are having those problems. So I would go down into my model and look at that. I can go ahead and explode out to stack tracing. Okay, and then here I can go through and look and see, as you can see here, this is standard profiling, and I could go down into my sections and look and see, you know, where is the most time being spent. It's pretty rad, you know, about the amount of information that you can get out of here. If you need help analyzing this information, you can actually compress, open a support case, and provide us with your SambaTune gen output. We can load it up in house and we can go through it together with you know. All right, you know, so that's one of the things that you can look at there. You also have a timeline explosion. Okay, I think I gotta drill down to see this. Whoops. Nothing selected, tap to see stuff. All right, I do not know why I'll be filing a defect against this. I do not know why this is not rendering the information. Oh, maybe. Oh, here we go. Just like that. Processes are showing there. Okay, sorry, live demo. I'll go through and file a engineering investigation to find out why that's not exactly working. All right, let's go back to our base analytics or back to our overview. We can then go through and, you know, this is, you know, more of the host, but we can go through and look at our drill down, you know, the amount of time. Let's go back to the overview and look at the RDU and see what it's doing on the RDU. So here you can go through, we're going to go through and we're going to go ahead and select all these just so I can show them all to you at once. All right. So here you can see this is our latency table showing you which section has the highest amount of latency. All right. Then you want to look at your PMU and PCU utilization. And it will go through and show you that by section. Now, one of the things that you're also going to want to do, remember how I said previously, like if you're greater than 90% PC utilization, you might want to break apart your sections some more and stuff like that. That doesn't mean that you want your PC utilizations to be down to 0 either. You want to try to consume as much of the PCUs as you can per section to really drive and optimize your utilization of the chips. All right. Here it's showing the PCI DDR. So in this particular case, section 2, which is the optimizer, is actually has the most DDR transfer time as far as D2R. So, and Darshan, you're gonna have to refresh me. D2R is the memory that's being transferred from the RDU back to the host, right? And then R2D is the other way.
Yes. D stands for device, which is the RDU device.
Yeah. Okay. Yeah. So in this particular case, more than likely we have an optimizer that's being computed on the host, and that's why we're having to send so much information back to it. You know. And here you can see this is really the way that you want stuff to go. You want to be, you know, transferring memory, you know, to the right effectively. All right. And then here's your just overall DDR write and read bandwidth per section. Okay. All righty. Let's go ahead. Let's go back to our dashboard. Now let's go ahead and compare two of them side by side. All right. So in this particular case, so the one that was the one that we were just looking at was on had a batch of 1024, mini batch of 128, 5120, and 512. Now here we're going ahead and we're splitting that effectively each one in half on the 10, 19, 16. So now we're going to go through and look at the analytics and compare them. Okay, so you will see here that in this particular case, it was 82% on host, 18% on RDU, 73% on host, 27% on RDU. So obviously the one that was run on at 1916, and by the way, I just filed an engineering investigation or a JIRA ticket to get this x-axis a little bit better. Right now it kind of overlaps. Let's see if we, yeah, even if you expand it out, you can, it's a little kind of hard to read. So I just opened up a JIRA ticket on that to get that a little bit better. Oh, one thing here, if you're doing a compare, you can't bring up your Pi instrument data because you can't, they can't overlay those two on a compare. All right, let's go back to our summary. Let's go down to the host. Here you can see that the later one, the one where we split the size of the batch size and split the size of the mini batch and split the size of the input and output features. All right, that's the second one in the dark blue. So it's taking less time in Samba, less time in the run setup, less time in the transfer, and less time in the com functions. All right, and over here you can see your savings and your latency by adjusting those items. And here you can look at your tensor thing, and you can see here how these tensors are, now like 75% less the size in bytes as far as the transfer. All right, now, mind you, now you've lowered your batch size and everything like that. You will obviously need to see, okay, is the slower throughput better with the larger batch size? Will that still get me through an epoch faster? Or is the faster throughput with the smaller batch size, will that get me through an epoch faster? So sometimes it is a little bit of a balancing act, but you can go through and look at the source data and then do the math and figure out, okay, which way is actually the more efficient way for me to run. So go ahead and look at our RDU utilization. And here's, you can see the latency obviously is a lot lower with the smaller sizes. Our section reports, which is, basically just showing you all the way breakdown per section. You can't do correlated reports across, I don't think. Oh, you can do your paths reports. So here it's actually showing you sort of like what internal functions are actually the ones that are, these are the ones that are taking the most time per section. And it's showing you how it's less. And if you look at it, each one of these is a buffer action. So that's a memory transfer or a tensor transfer. Anytime you see a buffer action, a G buffer is, like a data transfer, a T buffer is a tensor transfer. Correct me if I'm wrong, Darshan. I believe I have that right.
Okay.
All right. Okay, cool. And that's, well, yeah, here you can drill down on a per section basis. So here I'm in section 1 and we can go into the stage report. So now you can get down into the breakdown of that actual section into the individual little stages and drill it down. And once again, all this data is sitting there down in that reports file in either JSON or CSV format that if you want to play around with your own tools or, build a model that will analyze the output of a SambaTune run, feel free. All right.